sorry. Let's see if you can hear me now. Let's see. Testing, 1, 2. Here's that I have. Wonderful. Okay. So, welcome to our live stream today. This is the last live stream that I'll have before the test tomorrow for my students. And so I have a special treat for them. I have a copy of last semester's Calculus 1 final. And so we will go through this. And I am not able to show you the multiple choice questions because the multiple choice questions come from a test bank that we reuse. So we'll want to keep those secret. But I'm going to use the I'm going to show you the free response questions from last semester. I think that the best way to study for an exam is to look at old versions of the exam, and the most recent versions are probably most like the exam that you're going to actually see. So here is question 1 from exam number the final exam last semester. Is it not showing you? Oh, it is in fact showing. Oh, I also have to transfer the file over to my other on my other computer. Just a sec. Oh, it's unfortunate. Here we go. Okay, so that should allow me to. Okay. So the first question is, for what value of c is the following function continuous? I think we did a version of this previous live stream. Fascinating. Okay, so we have, for what values of c is this continuous? All we have to do is we have to figure out at what c value is the right and left side or are the right and left sides of the function equal to each other. So all we have to do is we're going to plug 2 into each of these functions. Notice we get an indeterminate form of 0 over 0 for our right side of this function. So we're going to have to factor and cancel. So let us show how to do that. We have f of x equals x squared minus 4 over x minus 2. When x is bigger than 2, we have 3x plus c when x is less than or equal to 2. So what that means is that we're going to let we're going to factor and cancel this top expression. So we get x minus 2 times x plus 4 over x minus 2. We cancel the x minus 2, gives x plus 4. And then when we plug in 2, we're going to get 6. Here, we get 3 times 2 plus c. We know that this side here, has to equal this side, which is equal to 6. We already found out. So we know this equals 6. 3 times 2 plus c equals 6 means 6 plus c equals 6, which means, of course, c is equal to 0. There we go. So, looking at our problem again, the answer to this problem is, in fact, 0. Okay, so the second question on this exam is going to be the graph. Oh, wait. This is the multiple choice. Never mind. We're going to skip all the way down to the free response questions. Looks like this is the free response question. So, for problems 17 and 18, we're going to have our function equals 6x plus 6 over x squared. And we're going to find where the function is increasing and decreasing. We're going to find where the function is concave up and concave down. Those are the two parts of our first problem. So we will do both of those on our scratch paper. So we have f of x equals 6x plus 6 over x squared. Now, the problem gave us a hint saying this is the same as 6 over x squared plus 6 over x, and that this will make taking the derivative easier. We will do exactly that. So this means that f prime of x equals negative 6 over x minus 12 over x cubed. That's the power rule on this chunk and the power rule on this chunk. We want to see where this equals 0 and where it's undefined. So let's set it equal to 0. That gives us negative 6 over x equals 12 over x cubed. Sorry, this should be squared. And this is cubed. That implies that x equals 0 is a critical point, because the function is undefined there. When we cross multiply, we get negative 6x cubed equals 12x squared. We will cancel off a square from both sides, and that implies that x equals negative 2. So this is also a critical point. These are the only two places where we can have the function switch signs. So that means that on our number line, we plot 0 and 2, and we need to figure out, are we increasing or decreasing on these three regions? Now, we can do this by plugging in points. That's a perfectly reasonable way of doing this. Looking at this, if I plug in, let's say we plug in 4, I get negative 6 over 4 squared. That's a negative number, and then a negative 12 over 4 cubed. That's also a negative number. Negative plus a negative is equal to a negative number, so that's negative in there. I look in here, if I plug in 1, I get negative 6 over 1 minus 12 over 1. That's still going to be negative, because that's still a negative over a negative, so it's negative there. If I plug in negative 1, I get negative 6 over negative 1 squared is positive 1, so this is a negative number. Negative 6 over... Okay, so negative 1 cubed is a negative number. That negative will cancel this negative and give a positive number. So I'll get positive 12, and I'll get negative 6. So I'm going to get a positive value there. So this tells us that our function is increasing here from negative infinity to 0, and decreasing between 0 and 2, and between 2 and infinity. So these are our intervals of increasing and decreasing. Okay, and then we have to do this to the second derivative to find the points where we are concave up and concave down. So we'll scroll just a little bit down. Now, the derivative of the derivative, so let's see, that'll be positive 12 over x cubed plus 36 over x to the fourth. That's our second derivative by the power rule. We set this equal to 0. That'll give us 12 over x cubed equals negative 36 over x to the fourth. That means that x equals 0 is a critical point. We cross multiply, we get, well, actually, we're going to cancel a 12, so that's going to be a 3 on this side. We're also going to cancel an x cubed, so that's just going to be an x here. So we get x, when we cross multiply, equals negative 3. And that's our other critical point. So we do the same thing. We draw a number line. Here's 0. Here's negative 3, and here's 0. We need to figure out where we're positive and negative on these intervals. So the easiest thing to do is going to be to plug in, say, 1, negative 1, and like maybe negative 5 or something. So going back to the second derivative, if we plug in 1, we get 12 plus 36 is positive, so we're positive in this interval. If we plug in negative 1, we get negative 12 plus 36, which is still positive in that interval. And if we plug in, well, if we plug in, say, negative 10 probably works. That'll be pretty easy to take. So that's negative 12 over 1,000 plus 36 over 10,000. So let's write that out. Negative 12 over 1,000. Negative 10 cubed is the negative 1,000. Plus 36 over 10,000. That's going to be the same as, well, we can multiply by 10 on the top and bottom. Negative 120 plus 36 is going to be negative. So we get a negative number over a positive number, which gives us a negative overall. So here is where we are concave down, concave up, and concave up on our function. Okay, so that one wasn't too bad. And now we move on to our next problem. We're going to write the definition. So here is our new problem. We're just asked to write the definition of derivative. And then after that, we're going to use the definition of derivative to compute. So the first part is the definition of derivative. The second is to set up the limit definition of a derivative for this specific function. And the third is to actually compute the derivative using that limit. So we will do all three parts of that now. So I forgot to switch to a different layer, so unfortunately it's a little bit tougher. This should work. There we go. Okay, so our function is x squared minus 3x. That's what we'll need later. What we need to do first is part A is writing the definition of the derivative. So that's the limit as h goes to 0 f of x plus h minus f of x over h. And then the second, so this is part A. Part B, we just plug in this function into the definition, so we get the limit as h goes to 0 of x plus h squared minus 3 times x plus h. This is our function with x plus h plugged into it. We want to subtract off our function. So that's x squared minus 3x. And then we divide by h. So this is part B, is just setting up this limit. Part C is actually computing this limit and plugging in 1 for x. So we're going to say this equals the limit as h goes to 0 of, we have x squared plus 2xh plus h squared minus 3x minus 3h minus x squared plus 3x all over h. That's going to cancel this term with this term and this term with this term. We're going to be able to factor out this h here. Factor out one of these, and one of these from the remaining 3 terms. So that gives us the limit as h goes to 0 of h times 2x plus h minus 3 all over h. These h's will cancel. And that gives us, now as h goes to 0, that goes to 0, we get 2x plus, minus 3. Which, if we use the power rule, we find out that is exactly what we should get, 2x minus 3. So, we have written the definition of derivative, we've plugged the function into the definition of derivative, and we have computed the derivative. The one last thing that we do have to do is we were asked specifically what is f prime of 1. Well, now that we have the derivative here, we can plug that into our, we can plug 1 into our derivative. We get 2 times 1 minus 3 equals negative 1, and that is our final answer to part C of the question. Okay, so now we go back to our problem set, and our next problem looks like a related rates problem. Okay, so water is being poured into a large storage container, the shape of a cone with height 3 meters and radius 3 meters. We gave you a picture so that you know the orientation of the cone. That is important. Here's our cone that I'm drawing. It says, if the water is poured in at a rate of 4 cubic meters per second, how fast is the water level in the cone rising at the moment the water reaches a height of 2 meters? And then it says, recall that the volume of a cone is V equals 1/3 pi r squared h. So, what we know is here is our cone. This is r. This is h. We know that r equals h, so that means that V equals 1/3 pi r squared h is equal to 1/3 pi r cubed in this particular cone's, for this particular cone. That gives us dv dt equals pi r squared dr dt. We know that dv dt, we're told, is 4 cubic meters per second flowing in. We have pi. We know that the radius, we're not given the radius. We're given the height of the water, or the depth of the water is equal to 2 meters. But we also know that the radius is equal to the height. So that means that the radius is also 2 meters. So we plug in 2 squared dr dt. The 4 here and the 4 here will cancel, leaving us 1 over pi equals dr dt as our rate that the radius is changing. Oh, are we asked? We were not asked for how the radius is changing. How fast is the water level in the cone rising? We're looking for dh dt. That's not too bad, though, because we know r equals h. So we take the derivative of both sides. We get dh dt equals dr dt. And we know dr dt is 1 over pi, so that means dh dt equals 1 over pi. Okay. So that's not too bad. Next question is, following the graph for g of x, so let me pull up our graph for us. The following is a graph for g of x. Suppose that capital G of x is the antiderivative of g of x that satisfies the condition g of 0 equals 1. Sketch a graph of g over the interval 0 to 6, labeling any maxima, minima, and inflection points. While your graph does not need to be perfect, it must reflect all of the important characteristics of the graph of g of x. Okay, so looking at this, what we know, okay, so wherever g of x is positive, we need capital G to be increasing. So from 0 to 3, we need to be increasing, and from 5 to 6, we also need to be increasing. So let us write that down. 0 to 3 and 5 to 6. We are increasing. And then we are decreasing between those. Also, we see that we have to be concave down between 0 and 1, 2 and 4, and that's it. So between 0 and 1 and 2 and 4, we are concave down. The reason why is because those are regions where g is decreasing, which means g prime is negative. G prime is G prime is capital G double prime. So the derivative of G is the second derivative of capital G. Where that's negative, we are concave down. Okay, so between 1 and 2 and 4 and 6, we have to be concave up for the same reason they were concave down in the other location. Okay, so now that we have that, we need to draw our graph. So let's see. Between, oh, we don't need to put the y-axis so much in the center. There we go. So we know that we have to hit the point 0, 1. And then what we know is that between 0 and 1, we are increasing and concave down. So let's see. Increasing concave down is shaped like this. So we want to be shaped like this until we hit 1. Then between 1 and 2, we are concave up and still increasing. That's going to be like that chunk. So we go up, and we might want to scroll there. Okay, this is between 1 and 2. Between 2 and 3, we are concave down and still increasing. So we will go like that. Need to clean this up just a little bit. So to there, and then to there. So this is increasing and concave down between 2 and 3. Between 3 and 4, we are going to be decreasing now, and we are going to be concave down between 3 and 4. Here's 3 and here's 4, decreasing and concave down. So like so, I go decreasing, concave down. We'll just I think I went a little steep there. There we go. Decreasing, concave down until 4. Between 4 and 5, we are concave up and decreasing, so we'll want to look like this chunk. That looks good. And then we want between 5 and 6, we're increasing, and concave up. So we'll look like that. This is our graph. So, we will see the next question. Oh, that looks like the last of our free response questions on this exam. So we'll go back to where we were last time on our other previous exams. Let's see. We were... Looks like 15 was the last question that we did. So we'll go on to 16 now. Oh, here we go. Okay, so we want to find the limit as x goes to 0 of x minus 1, let's see, times e to the x minus 1 over over x squared. Limit, here we go, as x goes to 0 of 1 minus x e to the x minus 1 over x squared. Okay, so if we plug in 0, we get 1 times 1 minus 1 is 0 on top, and we get 0 on the bottom, so this is a 0 over 0 indeterminate form. That means we're going to be able to use L'Hopital's rule. It looks like that's going to be the best solution. There we go. Limit as x goes to 0 of, we have a product rule here, so we have the first times the derivative of the second plus the second times the derivative of the first, and then the derivative of a constant is 0, so that's the minus 1 taken care of, and the derivative on the bottom is 2x. So now, when we plug in x goes to 0, we get e to the x minus e to the x over 0. Let's clean this up. So we get e to the x minus x e to the x minus e to the x. These will cancel, and then we get 2x. This x and this x will cancel. We have to make sure to write as our limit goes to 0, because this is a number, and without the limit it's a function. That's called a type mismatch error. So get the limit as x goes to 0 of negative e to the x over 2. We can plug 0 into this. We get negative 1 over 2, so negative 1/2 is our answer. Okay, so now we move on to our next question, which looks like it's an optimization question. Okay, so we have here an open at the top vertical tank has horizontal cross-section of an equilateral triangle and volume of 4,000 cubic feet. Find the dimensions that minimize the area, or the surface area. So this one is, I mean, most of these optimization questions are not particularly hard. We have an equilateral triangle. And let's see, equilateral triangle, it says hint, its height is root 3 over 2 times the length of its side. So if we have a side be x, that means that, okay, so we're going to look straight down on it. It looks like this. We know that this side is x. This height is going to be x root 3 over 2. That means that the area of this triangle, which is 1/2 base times height, area equals 1/2 times x root 3 over 2. That's going to be the area, but if we want the volume, we need the area of the triangle times the height of the cylinder. So the volume is going to be equal to x squared root 3 over 4 times the height. We also know that this is equal to 4,000. So that means that we can solve the height is equal to 16,000 over x squared root 3. This is important because now that we know the height, we know that the sides of this thing are just rectangles. So the height of the cylinder, the height of the prism is the height of one of the rectangles, and then the width of the rectangle is just going to be the side length of this equilateral triangle. So what that tells us is the surface area is equal to 3 times xh, which and plus the area of the bottom, which is going to be the area we already found. So x squared root 3 over 4h. That's the surface area. We're told that there's no top, but there is a bottom. So it's going to be the sides. There are 3 sides. They're all rectangles. So 3xh. And then the bottom is going to be x squared root 3 over 4h. That's the surface area of the whole thing. But we know what h is, so now we can substitute that in. We get 16,000 times 3 over x root 3. One of the x's in the bottom cancels with the x in the top. Plus, now the x squared cancels in the top and bottom here, and then a 4 cancels with the 16,000, giving us 4,000 root 3 over root 3. So I guess the root 3 cancels here too. So this root 3 cancels with that root 3. Okay, so that's our surface area. Let me double check that. Area of the triangle is the base. 1/2 base times height. The base is x, the side length is this, so we get, this is our area. Okay. Oh, that makes sense, because the height of the cylinder has nothing to do with the area of the bottom. Okay. So this is our surface area. And now we're going to take a derivative because we're trying to minimize it. So we get surface area prime is equal to, this is going to be negative 3 times 16,000 over x squared root 3 plus 0. We want to figure out where this equals 0, and it doesn't anywhere, but it does have a critical point at x equals 0. That is our critical point. You know, I feeling a little uncomfortable with this. I think I might have made a mistake, so we're just going to scratch that and start over. We have an equilateral triangle. Okay, and side of the equilateral triangle is x. The height, therefore, is going to be x squared 3 over 2. And that means that our area is equal to 1/2 times the base times the height, which is equal to x squared root 3 over 4. The volume is equal to 4,000, but is also equal to the area of the triangle times the height, which is equal to x squared h root 3 over 4. This gives us h is equal to 16,000 over x squared root 3. We know the surface area is equal to, there are 3 sides that are x wide and h tall, plus there's a base, which we already computed is x squared root 3 over 4. Ah, there's no h here. That's where we were getting weirdness. Okay, so the area of the bottom does not have an h in it, so I don't have to multiply by h later. Okay, that's great. So the derivative, and then we're going to substitute h here on this side, so we get 3 times 16,000 over x squared root 3 plus x squared root 3 over 4. That's our surface area. We take our derivative. Surface area prime equals -6 times 16,000 over x cubed root 3 plus x root 3 over 2 by the power rule. Okay, so now that we've got this, we set this equal to 0, and this will work better for us. So we get x root 3 over 2 equals -6 times 16,000 over x cubed root 3. This leads us to, when we cross multiply, we get x to the 4th times 3 equals -12. It's not a 12 times 16,000. We divide by 3. 4 here. We take a 4th root. Okay, so this 4th root, x equals, let's see, this is going to be 10 to the 3rd times 2 to the 1, 2, 3, 4, 5, 6. Ooh, that's not great, but okay. So we get, oh, and we don't have a negative sign here. When we move it to the other side, the negative sign cancels. Okay, so that means that x is equal to, looks like 2 times the 4th root of 4 times 1,000? 4,000? Okay. That is our x value. Our y value, well, let's see, find the dimensions. So we need to find the height now. So we take this x value, and we plug it into our height equation there. And that'll give us our height. So, yeah, that's how we do that problem. Okay, so let's look at our next problem. The next problem on our list is going to be, given the following graph for f, sketch f prime. So, looks like we have a cubic which means that our function, sorry, we have a cubic, so that means our derivative is going to be quadratic. And that's typically what happens. So we're going to have a two minimums. Look at our graph here. Notice that we have what looks to be a sorry. That's the graph of f. We're looking for f prime. So what we need to have since we have a maximum and a minimum at -1 and 1, that means that our derivative will have zeros at -1 and 1. Since we are decreasing between x is -1 and x is +1, we're going to have a negative derivative between those. And so what looks like we're going to get is a function that looks something like this. We have a 0 here at -1, a 0 here at 1. We have our lowest point here. That's where we switch concavity. And we get something that looks kind of like this for our derivative. Notice that we're increasing on the outsides of our interval here. We're decreasing on the inside of the interval, -1 to 1. We switch from being negative slope to positive slope at 0. That reflects in the graph of the original function by saying that the function is definitely increasing when x is less than -1 and when x is greater than 1. And it's decreasing between the two, so that matches the derivative. But also, we have the function is concave down on negative values of x and concave up on positive values of x. That's reflected by having the derivative be decreasing on negative values of x and increasing on positive values of x. So, so that's how we do that function. That's about as much as we would be expected to do. Now we have the next question is we're going to do an epsilon delta limit proof. We don't actually do those anymore in 112, especially not on the final. So we're going to skip over that question. So our next question is going to be approximate the integral from 1 to 5 of x to the 4th dx using a left-hand sum with two subintervals. So n equals 2. Okay. So let's do that. We have the integral from, was it 1 to 5? Yes, it's 1 to 5 of x to the 4th dx. Now we want to use two intervals. So that means that we want the distance from a to b is 4. So if we're doing two intervals, each interval has to be 2 units wide. That's our delta x. b minus a over n equals delta x, which in this case is going to be 5 minus 1 over 2 equals 2. And we multiply that by the left endpoints of each interval. So the left endpoint of this interval is going to be, the left endpoint of the first interval is going to be at 1, and the left endpoint of the second interval is going to be at 3. So 3 to the 4th is 81. So if we looked at a number line, here's 1, here's 5, the midpoint is 3. This is the left endpoint of the first interval, and this is the left endpoint of the second interval. So we go f of 1 plus f of 3 gives us the heights of our two rectangles. So 1 to the fourth is 1, 3 to the fourth is 81. The width of the rectangles gives us our approximation. So we get 1 plus 81 is 82, times 2 is going to be 164. That is the approximation that we get using two rectangles. Okay, so our next question says, find the area under the function f of x equals the cube root of x from 1 to 8. So that just means we're doing an integral from 1 to 8 of x to the 1/3 power. This is not too hard to do. We can do it using the power rule. So we get x to the, we add 1 to the power, getting 4/3. We divide by the new power, which is 3/4. All right. Divide by the power 4/3 is the same as multiplying by 3/4. We evaluate at 1 and 8. We get 3/4 of 8 to the 4/3. So the third root of 8 is 2. 2 to the fourth is 16. Minus, we have, well, any power of 1 is going to be 1. So we get 3/4 of 16 minus 1, which is going to be, let's see, 45/4, I think. 16 minus 1 is 15. 15 times 3 is 45. So this, which is 11.25. So that's not so hard to compute. Going back to our problem list, we have another epsilon delta question, which we will skip. Let's see. Which of the following is an inflection point of f of x equals x over x squared plus 1? So f of x equals x over x squared plus 1. We want to find the second derivative to find the inflection points. So we get f prime of x equals the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over square of the denominator. This is our first derivative. We will simplify because we're going to continue on to find another derivative. So we get x squared plus 1 minus 2x squared over x squared plus 1 squared, which equals negative x squared plus 1 over x squared plus 1 squared. And we might as well factor out a negative sign from here. So we're going to get negative x squared minus 1 in the top. Okay, so the second derivative we can do using the quotient rule again, or we can use logarithmic differentiation. I'm thinking that we want to, let's say, we'll use the quotient rule again. So we have negative, we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over, sorry, clean this up, a negative sign out in front of the out in front of the fraction. And then squaring a square gives us to the fourth power. This here is our second derivative. We need to figure out where this thing has roots and asymptotes. The denominator has no roots or asymptotes. So, the denominator has no roots, so this function has no asymptotes. So that means that we just set the numerator equal to 0. So from here, we want to simplify. We're we're going to have to multiply everything out. So we got x to the fourth plus 2x squared plus 1 times 2x minus x squared minus 1 times 4x cubed plus 4x, 0. Multiply this out, we get 2x to the fifth plus 4x to the third plus 2x minus, looks like 4x to the fifth plus 4x cubed minus 4x cubed plus 4x. So this negative sign cancels with this negative sign on the last term. This negative sign cancels with this negative sign on this middle term. There's a negative sign on this middle term, and then this side, this multiplication has a negative sign on it. So there we go. And then we're gonna cancel. So this cancels with that. And let's see what else cancels. Okay. So looks like we get 2x to the fifth, negative 2x to the fifth, because this term and this term connect. Negative 2x to the fifth plus 4x cubed plus 6x equals 0. That means x equals 0. We can factor out a negative 2 from everything. So we're going to get, looks like x the fourth minus 2x squared minus 3 equals 0. And we can use the quadratic formula on that. Okay, so we get x squared equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, which equals, let's see, 1 plus or minus square root of 16 over 2. That's going to equal 1 plus or minus square root of 16 is 4. 4 over 2 is 2, which is going to be negative 1 or 3. But we can't take the square root of negative 1. So x equals plus or minus the square root of 3. Those are our inflection points. Well, those are our possible inflection points. So we actually have to check now. We have negative square root 3, square root 3. We want to check where does the second derivative switch signs. So this derivative. So let's plug in 0. We get this is 0, and this is 0 over 1. So that didn't help. Oh yeah, we also got this 0 here. So that's another critical point, or possible critical point. So let's plug in 1 now, see what we get. Plug in 1, we get this is a positive number, this is a positive number. We get 2 times 2 is 4, and we get 0. So we get 4 on top, we get a positive number. At the bottom of the thing is negative there, so negative. Let's plug in like 10. We get 101 times 20. We get 100 minus 1 is 99. We get is a big number, so looks like, oh, but this is also a big number. A really big number. So let's see. Well, actually at this point, it's not really calculus anymore. We have our intervals. We just want to plug in values to see where these intervals are positive and negative. We found this one is negative. I bet that this one is positive, so let's try plugging that in just to see. Get -1 squared is 1, plus 1 is 2. This is -2, so 2 times -2 is -4. We get 0 here, so we get -4 on top. We get a positive number on the bottom. Negative times negative over positive is positive, so we get a positive value here. That tells us that 0 is in fact a critical point, because an inflection point, because the second derivative did change signs on the two sides of it. So we just keep plugging in points and we'll get positive and negatives values. And if we switch signs at one of these, it's a critical point. If we don't switch signs, it's not. So that's not too bad. But it's not calculus anymore, so we will move on to our next question. So our next question is, given that x ln y minus y ln x equals e squared minus 2e, find dy dx at the point e squared, comma e. I think that the older exams are harder than the newer ones. So let's take a look at that. We have, let's see, y ln x. Oh, we have x ln y minus y ln x is equal to e squared minus e. Let's see. And now, from here, we want to look at the point e squared comma e. So we take a derivative. We get ln y plus x y prime over y minus y prime ln x minus y over x equals 0. That's just the derivative using our implicit differentiation. We plug in our point, so we get ln e plus e squared y prime over e minus y prime ln e squared minus e over e squared equals 0. This here is 1. This here cancels. And this is 2. And this cancels like so. So we get 1 plus e y prime minus 2y prime minus 1 over e equals 0. We get y prime times e minus 2 equals 1 over e minus 1. And that gives us y prime equals 1 over e minus 1 over e minus 2. This is the slope of our tangent line. And that is an hour. So good luck to all of you on the exam tomorrow. And yeah, best of luck. Bye.